All right. Good morning. I hope you had a pleasant evening and a refreshing night. Our next talk is by Kai Michaelis of Immune GmbH with a talk called The Black Box in Your Data Center.
Okay, so yeah, good morning from me. First talk on the last day, 9 o'clock in the morning. So something light to wake up to. I promise I'm not going to show any code or something like that. Just a light talk in the beginning. So yeah, I'm Kai. I'm a CTO at Immune GmbH, which is a tech startup. We do, who would have thought, firmware security. I previously was a firmware developer and did crypto implementation. And also analysis. And well, I care a lot about cryptography, static program analysis, security. And well, if you go into the firmware development from this like more security-focused education, there are a lot of new things there, and it's surprising how other people do stuff, and it actually works. So okay, let's talk cloud, right? Let's talk about data centers. And you may have noticed, but the age of desktop computers is over. These little boxes that we have on our desks, where all data was in, and we could just go there as long as electricity was available and use our data, do our computing. That's over, right? And this is never coming back. Internet connections are fast enough, so we can put our data and compute into the cloud, which is just other people's servers. And this is a pretty heterogeneous landscape there. So it's not just an Intel CPU running in a big box. There's a lot of stuff there. And we as defenders should focus more on the security of these systems because all the data is over there, right? The client has access to the data, but not of everything. So it makes sense to take care of the security of these servers. And so we go in our data center, or maybe if you're not so big in our co-location space place, pull out one of our servers, open the hood. Okay, what's in there? And it turns out it's actually a distributed system. Well, first there are lots of CPUs in there that talk to each other, but I mean, our mobile phones also have that. But there's other stuff there, not just Xeon CPUs, right? If you have one of these super fancy Mellanox network cards, they run a whole operating system that can do routing decisions on their own without interfering with the host CPU. If you have a compute system, you probably have graphics cards on there to do like performance computing. And graphics cards are not just frame buffers you write into and then they display it, right? So you have shader units there. And even if you upload the shader program, you're not talking to the shader units directly, right? You're talking to an ARM CPU that does all the scheduling and resource allocation, stuff like that, right? There's a complete operating system in there. They actually use UEFI to boot these graphics cards. So you have a complete system in there. You probably have heard of the basement management controller like ILO or iDRUG or BMC from Supermicro. These also run complete operating systems, have access to the PCI bus, to SPI bus, monitoring of the system. They often have like graphics cards in them, so you can use them as KVM for Windows. Lots of stuff in there. And even if you ignore these like complex systems, you have things like smart voltage regulators or embedded controllers to turn LEDs on and off, figure out whether things are connected or not. And all of these things, they all run software. It's mostly written in C. They all expose interfaces to the host system, which means they all can be attacked. Okay, so when we look at the classical view of okay, what's on the stack of our systems, we start with the bootloader, right? The bootloader like grub2 starts up, or maybe with the Windows bootloader, and then loads a hypervisor like VMware, Xen, maybe Debian with KVM, Hyper-V if you're one of those guys. And the hypervisor starts virtual machines. Virtual machines have an operating system in them that are hopefully minimal, and then applications run. Right? And this is where our focus is, right? We look at the applications, make sure they are bug-free. Then we maybe look at the operating system, okay, is this minimal? And then we hope that the hypervisors, these big buggy C programs we run there are okay and provide some kind of isolation between these operating systems. But we don't talk about all the firmware that's on these systems that is still running, right, and has still access to the memory via DMA, for example, the complete system state using the system management mode, things like that, right? So the firmware is complete black box. We don't know what's running there, what's the versions, who built that, how can it interact with my system. And I think, especially for server security, we have to take care of firmware. We have to make sure that we have this under control. And this is sort of the core message here I want you guys to take home. You have to take care of firmware. Okay, firmware, I mean, how bad could it be, right? So, after we put off our server off the rack, we get our screwdriver and disassemble it, get the board out, and look at the board and see what's on there, right? We ignore the Mellanox cards and all that stuff like that, right? Just ripped it all out. What's on our board here? And as we start from the bottom here, we have the BMC firmware I talked about, right? So this is probably the most visual thing we can imagine. Is like ILO, iDRAC. These systems are the exposed network interfaces. You can use them to manage the system. Obviously, there are not complete operating systems, proprietary operating systems. And all of these, like the ILO, the iDRAC, they all had CVEs with the perfect 10 score, right? Unauthenticated remote code execution over the network, right? In the internet. So ILO had this in 2014, two of them actually, Supermacro and iDRAC, which is Dell, I think, had them both in 2019. And I promise you, this won't be the last, right? There's lots of stuff in there. And these, most of the time, are actually exposed to the internet. So that's a problem. Then we have the UEFI firmware, which is what we previously called the BIOS. And we'll talk about that later, but that's also on there. We have the PCH, which is what we previously called the source bridge. So in case you went to university, you may remember in your CPU operating system architecture class, they talked about the source bridge, or maybe you yourself taught and read about it in books. The source bridge does I/O. Like, okay, the CPU can talk to the PCI bus, can talk to the SPI bus, so that's what the source bridge does. And this is still true, but not only I/O. So the PCH, for example, hosts the CSME, or what's previously called DME or SPS, which is also now a completely separate operating system from Intel that can actually run third-party code. So if you're buddies with Intel and have a good use case, they will sign your blob, and then you can load it using the DAL, the Dynamic Application Loader. So your ME is possibly running third-party code. Pretty cool. It also has access to everything, right? It can on the BIOS directly talk to the CPU over a proprietary interface, and because it's in the middle between the CPU and the I/O interfaces, it can pretty much intercept everything. Then we have PCI option ROMs. You may remember these things, may have heard of them. So PCI has a feature where each PCI card can expose a binary blob to the host system at boot that the host system will read out, put into memory, and execute. And these blobs initially were actually 16-bit real mode applications. So they're running without any security enabled, right? No paging, nothing, right? We execute them and that's it. Nowadays, there are UEFI applications, so they have some kind of structure. They can be signed in theory. They're actually 32 bits, but you can't really enable security features because they need to have access to the PCI bus, for example, in order to initialization of the card. And now you think, okay, I mean, PCI, you have to open the case, put a custom PCI card in to attack me, so how realistic is this? Well, there's something called Thunderbolt, you probably heard of that, that looks like USB, but it's actually PCI Express, and has all the features of PCI Express, including the option ROM feature, and this was actually previously used to attack an earlier version of Apple MacBooks. So I can, like James Bondy type, can put in a special thumb drive into your Thunderbolt and boot up the system and read out the PCI option ROM. And if it's signed by someone, it will be executed at pretty much highest privilege levels you can imagine. Then we have the TPM on there, which is a security feature. I will talk about this later, but I mean, with all add-on stuff, it also runs software. It also can be attacked. It can't run third-party software, at least not without exploits. But there's still a lot of code in there. You can actually update it, so you can get software in there that you have manipulated. And if you have one of these super fancy Sapphire Rapids Intel CPU boards, you will have a FPGA on there that also does security, called the PFR. And this also contains its custom bit stream that's also on the flash, can be updated, can be changed. And this actually runs before even the PCH is on, right? You have the FPGA running, then you have the source bridge and the CPU starting. And again, these all exposed interfaces, they all run software, so they all can be attacked. Okay, UEFI. Maybe a bit information. Okay, what is UEFI? Because that's a large attack surface there. Again, if you maybe remember from the previous days at university, the BIOS needs to initialize the system. So if you start with your Xeon CPU, it will start in a 16-bit real mode compatible mode, so you can run your MS-DOS applications without modifications. So in order to get the system in a state where you can actually use for things like start Windows, you actually have to enable 30-bit, 64-bit, enable paging, set up interrupt routines, stuff like that, right? This is what the BIOS is supposed to do, right? And this is also what the UEFI does. This is what here on the right side, these three little boxes, the processor in it, the chipset in it, the board in it. So this is what we imagine our BIOS would do. But this is the pre-UEFI initialization phase, right? This is the early stuff. After that, we have the DXE phase. So UEFI has a concept of an DXE driver, which is an application that exposes interfaces that can require interfaces that are implemented by other DXEs. And then you can imagine that there's, for example, a DXE file that would want to boot an operating system off the disk. So it would say, okay, I'm the boot DXE. Please give me an interface that implements the like read from hard disk interface, and maybe an implementation of X2 or whatever file system you have in there. And the base layer of UEFI would then find these DXEs that implement those interfaces, boot them up, initialize them, and provide these interfaces. And they would maybe need other interfaces and so on. So you have this network of DXE drivers calling each other, initializing stuff, doing things. They all expose an UEFI interface to the operating system. So even after the system has been booted, there are still UEFI stuff remaining in the memory because the operating system needs to access information of the UEFI, for example, the memory layer of the system. So it's not just gone after boot. And well, after DXE phase is over, we have the boot manager. The boot manager actually loads the operating system or your hypervisor or whatever. And yeah, then you have your system started. These DXEs, right? They implement pretty much everything you could imagine. There's a network stack in there. There's HTTPS in there. There's TLS in there. There are JSON parsers in there. Everything you can imagine. Which begs the question: who builds these operating systems? Well, a lot of people. So if you go to Dell or Lenovo to get your new Lenovo laptop or Dell laptop, they don't build these things, right? They don't build hardware. What they have is they have the stores and they have the salespeople. If they want to build a system, they go to companies you probably never heard of, like Vwin or Quanta. They are hardware companies. They build stuff, right? They can do the board layouts, they do the manufacturing, they can do the sourcing, stuff like that. So Lenovo goes to Quantas, say, okay, please build me a new T, whatever. And they build the hardware, but these are hardware companies, right? They don't do software, they don't want to do software. So in order to, but they need software for the system. So they go to American Megatrends or Phoenix, and they provide them with the BIOS and all the provisioning tools around it, right? Because you can't just flash stuff on the flash chip and be done with it, right? You need to provision your CSME, you need to fuse keys in there to do signature verification, stuff like that. So this is what American Megatrends and Phoenix build. But they don't build it completely by themselves. What they actually do is to take the reference code that's written by Intel, a bunch of blobs that come from Intel that do like CPU initialization, memory link training, the super early stuff, combine it all, and then add their value add on top of that, right? Because otherwise they would just sell the same thing. AMI would sell the same thing at Phoenix. There's no way to differentiate themselves from each other. So in order to do that, they add value add, right? Bloat, maybe someone would say. Okay, so what's the problem with that, right? I mean, okay, it's a lot of code. It's fine. I mean, I need to boot up my system. So if you open up one of your Flash images and look what's in your UEFI, thankfully there is some structure, right? The UEFI isn't actually open specification. So you can actually disassembly things, see, okay, what DXE drivers are in there, what do they do? You will see, well, you will find a lot of stuff, right? There's stuff like here, the things that they look okay, fine, like the boot device driver, or maybe, what do we have here? The memory info protocol, okay, sounds necessary. Then there's stuff like the UEFI debug port protocol in there. Why would I want that for a production system? Sounds kind of dangerous. And there's stuff from AMI here. This is one of the evaluate stuff. There's the AMI CPU info protocol and an AMI CPU info 2 protocol. I wonder what that does. And there's stuff like the SMM initialization. So SMM is a feature of the CPU that allows you to run extremely privileged code in a hidden memory area that remains after the system has been booted. And this code is always activated when a special interrupt is called. The CPU will stop all other CPUs, so the application CPU will stop, the bootstrap CPU will stop all other CPUs, execute the stuff that's in system management mode, and after system management mode has returned, the CPU continues on. And the SMM has access to pretty much everything, right? And the UEFI is the code that actually injects this SMM code in there. It's impossible to even inspect it, right, because it's hidden, you can't read it out. And this is one of these Dixie files, there's somewhere here that does that here, the SMM control. You don't really need SMM. It's more for legacy reasons in there. So you can really disable it. It's one of these value add stuff that comes from AMI. Well, this is your trusted computing base here. The UEFI doesn't have any really security mechanisms. You have, of course, these Dixie files. You have paging enabled at that point, but this pretty much identity mapped the whole memory. So everything that's in there is your trusted computing base that can inject stuff into SMM. It can access the flash because that's not locked at this point. This is a gigantic problem. You can't and you can't really remove it because it's all proprietary, right? You don't know how things interact here. If you just throw out one of these, your system probably doesn't boot anymore. Another problem with this like chain between Intel and the BIOS vendors and us is that the documentation that's out there that's not NDA'd from Intel isn't the whole truth, right? So for example, here this guy found out that the system management mode I talked earlier before can actually bypass lock bits. So there's a special register in the CPU that controls what features are enabled in the Intel CPU and what are disabled. And how it works is that when it starts up, there are bits for pretty much every feature in there, and there's a lock bit. And the lock bit is 0. And at that point, you can write into it and read and enable things, right? And after the UEFI is done, before it calls into the operating system, it will set lock bit to 1. And now the register is still readable, but not writable. So you can't disable features. Turns out, the system management mode can just bypass the lock bit and disable security features of your CPU, which is actually a problem, right? Because if we as defenders don't even know what the SMM has, the capabilities of an SMM, it's not even possible for us to gauge, okay, how much do I have to trust certain pieces of code, right? Now I have to trust the UEFI even more because it's able to inject code in the SMM. There are lots of examples of that. And lastly is most of the initialization code of your CPU comes actually from Intel. It's all proprietary blobs. So for example, here's the FSP, the firmware support package, that you need in order to do memory training and board initialization. This comes directly from Intel. It's 2.4 megabytes, and it's just binary blob data, code and data, and you have to call it in various stages of the boot cycle to do init, right? You can configure it in a bit, but mostly you call into it, it runs, it returns, and does initialization stuff, right? And you can't get around it, right? Whatever this thing does, it's not open. Which means that these server systems that we trust so much, right, on the firmware that's running on there is completely intransparent. It's completely unclear, okay, who built the UEFI components we saw earlier, right? So not everything there comes from AMI. Maybe AMI gets it from somebody else. Maybe it comes from Intel. Maybe Intel got it from somebody else. Nobody knows, right? It's just a blob that gets dumped into your flash memory. We don't really know what these things are capable of, right? Because lots of documentation is under NDA, and the documentation that's out there straight up lies to us, right? Like in the SMM mode. And all of this means that open source firmware is still a rarity here, And in order to illustrate how great lengths people go to get an open system, so if you say, okay, I don't care, I want an open x86 laptop, right, without all the proprietary firmware. Your best bet is to get an X200, which is a ThinkPad from 2008. This was the last generation that was actually able to run without ME. And these things are still sold, right? I have one of those. I can't recommend having one. But yeah, they're still sold. And this is your best bet if you want an actual open system running x86. Another problem is, so these platforms, they all have platform security features that could help us to at least lower the amount of trust we have to put into the UEFI implementations. But it's often unclear which of these features are actually enabled on what platform. Because Intel ships the CPU with pretty much all features in there, but what to enable and how to enable it depends on the OEM, right? So they can disable certain features using configuration files in the flash. And well, if you call up your vendor and say, hey, I would like to have a CPU on a board with TXT-nail, for example, they probably won't even know what you're talking about. So it's always hard to get servers with specific security features. Okay, sounds bad. Why do I care, right? Who gives a F? Okay, it's early, so let's do a bit of back of the envelope calculation, right? So this is a bit silly, but bear with me here. If you get one of these servers and add up all the flash chips you have on there, you come up with like a 1/4 gigabyte of space on there, which means like 256 megabytes of code that just comes with your system, right? You can't disable it. You can reinstall that stuff. This just comes with the system. And there are studies that show that, okay, around 1 million lines of C code result in 60 megabytes of like assembly binary code. And we know, if we read our code complete, we know that we have in production code, right, stuff that's released, that has been tested and is released, we have pretty much one bug every 2,000 lines of okay quality code. Which means that the system, as it comes out of the factory into your data center, has roughly 8,000 bugs. How many of them have been found already? I don't know. How many of them are actually security relevant is an open question, just to give you an estimate. So 8,000 bugs just right off the factory. Here are two of them. These are both from this year. The Intel BSSA advisory. What the BSSA is one of these blobs that you get from Intel. I think it does some debugging stuff. I'm not super sure on that. Thing is, Intel shipped this, if you remember the timeline I saw you, right? The value chain, right? Intel shipped that blob to the BIOS vendor. The BIOS vendors got a request from outside, say, hey, please give me a firmware I need for this board. So they took their implementation they have, didn't fork. They don't really do forks because some of them don't have source control. But imagine they had source control, they would do a fork. There would this BSSA blob would be in there. They would ship it off, do the board in it, ship it off, and now it's in the board. It's flashed on the system. That's sold to you. Now Intel has to tell AMI, hey, you have a bug in this and that blob. Now AMI has to figure out, okay, which of these systems we shipped out includes that, and this is a hard problem for these guys, right? And even if they manage to do that, they now have to tell the hardware vendors that know anything about software to contact Lenovo to tell them, hey, these systems you have there, they need to be updated. And if another 3 years go by, nobody will do this anymore because all these support contracts are expired and they're already gone to new products, right? So nobody will update this. This isn't forever day. The other one in the bottom, the same. This other bug in the reference implementation, in the open source reference implementation of UEFI called Tiana Core. Both of them are local privilege escalation. So if you have local ring 0 privileges, you can escalate them to A5 privileges, which is the highest thing. At this point, you can inject SMM code and persist pretty much in Flash, right? Completely undetected. And I say, okay, well, local privilege escalation. You need to be root. I mean, how realistic is this? Here's one from Dell. So Dell has a super feature in his UEFIs where using local proxy, the UEFI can actually connect through the browser to servers from Dell. So Dell can figure out, okay, if you're on their support page, what version is this guy running, what's the hardware, and actually update the UEFI through your browser over remote. Well, it turns out that the TLS connection they use can be man-in-the-middle, so I can update your UEFI over the network and gain access to that. So these are 3 of the 8,000 bugs, right? Okay, if we take a step back and think about, okay, what's the timeline here? We saw the first weaponized UEFI malware in 2012. This was the CIA leak, Vault 7, where the CIA developed something called the sonic screwdriver, which was still hardware. So it's, if I understand correctly, it's like a USB key you put into the laptop. There's some UEFI stuff on there, the laptop boots off that, and you have malware in your system on the flash chip. After that, we saw in the hacking team leak in 2015 the first actually commercial rootkit that used a repurposed like theft prevention remote wipe UEFI product. They repurposed that as malware. So hacking team used that, or at least solved that, and we know that in 2017 a derivative of that was used to attack the DNC in the US. So we have in 2017 the first like actually documented attack using UEFI vulnerabilities. And now fast forward, it's 2001. These are from 2020 here. Like LoJack is one of these repurposed theft prevention tools. Now these are used by standard commercial hackers like organized crime. For example, TrickBot is one of these exploits kits that are used to steal your credentials and whatever. And we went from, and they have now a UEFI component. So we went from super James Bondy stuff, like you have to connect a USB stick while the guy is away from his laptop, and then you have to boot it up, and then it's backdoored. We got very from that to UEFI malware just being another tool in the toolbox for organized crime in roughly 5 years, right? So it's coming nearer and nearer, right? This is still custom software, but you can imagine that will take a few years, and then every pedestrian hacker will have the ability to use UEFI vulnerabilities. Especially if more people look at that, right? When they see, okay, here's some effective way to persist. Okay, why do we care? Yeah, all right. Sorry. So this is all terrible. I'm not a fan of these everything's terrible talks. So we should think about, okay, what can we do about that, right? And I'm a fan of doing the easiest thing first. And the easiest thing first is to increase visibility in our firmware, right? We need some kind of firmware monitoring, firmware analysis. We say, okay, we have to figure out, okay, what's running on my system, how it's configured, is it configured correctly, and take this into consideration when we're dealing with servers. So there are a few tools for that. ChipSec is the oldest one. This was actually developed with support from Intel that checks known attack vectors, known vulnerabilities, known malware in your system. It's a bit difficult to use because the UEFI application, at least last time I checked, so you have to boot into ChipSec in order to use it. There are easier tools like the Converged Security Suite. I was involved in the development of that a bit. That is able to do this pretty much the same analysis, not the same checks, but similar analysis on data you read out of the system, and then later analyze on somewhere else. And well, if you're super into it, you can also use a UEFI tool, which implements the UEFI specification to disassemble your UEFI and look, okay, what DXY files are in there, what's weird, maybe try to remove one of them, see if it still boots, things like that. But yeah, it makes sense, I think, to start with the monitoring here and do at least some blacklisting of known problems. So maybe a call to action for you guys. So next time you want to buy a new server or a new batch of servers for your data center, and get samples from various vendors instead of just checking the performance of these systems and how nice they feel. Maybe run chipsec and take the one with the least problems. At least take this into consideration. Then we can do remote attestation. Just briefly about this, the idea here is that we record what's booting on the system without interfering with it, just recording. And saving the record, most of the time it's just a cryptographic checksum, on a separate component that ideally an attacker cannot access. And then later doing a remote attestation where he asks this component, hey, what has been booted? And depending on what you get back, right, you get a bunch of hashes back. You can decide, okay, is this what I expected, right? In the easiest way, would we say, okay, is this the same stuff that has been booted last time? And if not, did I update the system? If you didn't, maybe check out what's happening there, right? Maybe do an update. The problem with this is, so there are a few implementations. There's the PFR I talked about, which is a bit more modern, and there's the older TPM2 implementation that are also available for virtual machines. So Google will sell you a shielded VM, which uses a virtualized TPM that's secured by the hypervisor to do that. These are pretty cool, but there's no ready-made solution yet. You can just use. So there's still a lot of integration required. And now for the actual solution here. It's open source firmware, right? We have to get open source in that area. And I honestly believe that the model that AMI and Phoenix currently runs, right, where you sell proprietary UEFI, a proprietary operating system, will in less than 10 years be as commercially viable as selling compilers nowadays, right? I think open source will take over that area, like it took over the operating system market. There are a few projects to look out for. Coreboot is the first one. So the idea of Coreboot is not the UEFI. The idea of Coreboot is more like the BIOS, where we say, okay, we do the absolute basic bare bones initialization of your CPU, just enough that you can run Linux. And then you read Linux, get Linux off the flash, have a special Linux distribution with the InRD compiled in, and use that for your initialization stuff, right? That's the problem with UEFI, right? You can say, okay, JSON parser. Who cares, right? I don't need the JSON parser in my UEFI, in my firmware. Well, HTTP boot is actually pretty cool, right? It's definitely less annoying than setting up a TFTP server, and it's also more secure, right? You can TLS. So we need the functionality, but what we don't need is to build a complete proprietary operating system just for that functionality. Just use the operating system we already have called Linux. There are some ways to get an open source server nowadays. So there's an HPA Alpha program, especially provided ProLine server that you can actually put Linux boot on the system via the BMC. It will still run UEFI, but after that we boot in Linux boot and you can actually do custom stuff. And there's the Open Compute project that actually does open hardware for hyperscalers. And there are resellers like AttuneU and Sesame that will sell you less than a rack. So normally you go there and buy a whole data center. But if you want just one server, you can go to AttuneU, for example. And they sell you a system that will be actually running Coreboot on Linux boot. So this is the only shill slide of my talk, I promise. If you are into open source or you think this is a problem here, you are interested, we're starting an Open Source Firmware Foundation, where we try to do exactly what I said earlier, right? Get open source into the data center market, get open source into the firmware, right? You need to do a lot of stuff, right? You need to support the projects. You need to explain to C-level executives to why open source makes sense, right? Why it's cheaper. This is all obvious stuff for us, right? We've seen how Linux destroyed the commercial Unix market, right? This is obvious. It's just cheaper and it's the better development model. But you have to explain this to people in the hardware business that don't know software, that haven't seen what we really have seen, right? And that's the idea of this Open Source Firmware Foundation. We have a very strong focus on security. So we have a security track where we try to define standards. Okay, how do you do open source firmware but securely, right? How do you exchange, for example, information about malware, like this is happening on the antivirus side of things, things like that. So if you're interested, we are called Open Source Firmware Foundation. You can just Google it. We're the only ones. We also have a conference in end of November called the Open Source Firmware Conference. You can find it on Google. We are online, so you can just watch it online if you want to. Okay, so in case you fell asleep, it's now time to wake up. What I want to tell you here is, the only have to take away from here is, firmware is a black box. Firmware is becoming a threat. We have to take care of that. I understand that you probably have other things to take care of too, like ransomware, but we have to take care of our firmware. Keep this in mind. This will become a problem in less than 5 years. Thank you.
Thank you, Kai, for this very insightful and concerning talk. Do we have any questions from the audience?
So thanks for the great talk. I would ask, when do you think will be like the first really commercial open source firmware server available? I mean, there is the internal project from Google and from Facebook, their Linux boot, I think. But when do you think will be for the broader mass available? Do you have some ideas or estimations?
I would say a few years. So you can already buy these open compute systems. They are refurbished, meaning they are like 3 years old, right? And they are weird. But yeah, you can buy them already. You can actually buy Purism servers. So Purism will sell you a 5-year-old Broadwell DE platform for like $3,000. So if you're super concerned about open source, you can actually get that. But yeah, we see a lot of traction there. We know, I talked to other hardware vendors, and you have to try to explain to them, but they have customers coming to them, tell them, hey, do you guys do open source? So there is traction there. The hyperscalers, they are already on the open source track, and everybody else will follow. So I would say a few years.
We have another question here. Oh, sorry, okay, misunderstanding. In that case, I also have a question. I was wondering, do you know of any hosting providers, cloud providers that are already using open source software and firmware?
I don't think so. There are cloud providers who use OCP hardware, but they don't advertise that, and I don't know what firmware they're running. No, sorry, I don't know about that.
Okay, do we have any more questions? Okay. In that case, thank you very much.
Thank you.
Michaelis.